Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling maximum and minimum values, and that is because we're headed in this direction where we want to talk about optimization, right? We want to start answering questions like, what's the shape of a can that minimizes manufacturing costs? What's the max acceleration of the space shuttle? What is the radius of a contracted windpipe that expels air most rapidly during a cough? And what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? Now, these are all extreme applications of optimization. Like, this is where you would use them in the kind of the real world situation. And we're not going to necessarily answer these exact types of questions. But the point I'm trying to make here is that differential calculus can actually help you solve questions like this. And they're called optimization problems. But in order for us to do that, right, in order for us to look at how to optimize something, which is finding maximum values of a graph or minimum values of a graph, depending on what it is you're trying to do, then we need to recap extrema. We need to remember how to deal with finding the extrema of particular functions. There's 4 types of extrema. There's absolute max, absolute min, local max, and local min. And I gave us an example of where those exist in this particular graph here. Like, this is an absolute max, that's an absolute min, this is a local max, this is a local min. But the thing to highlight in this slide is the fact that the extrema themselves are f values, which means they're y values. If what we're talking about are high points and low points, we mean that in a kind of a physical sense, right? Literally high and literally low points on the graph itself means that we have to be talking about verticality of a graph, and that's what the y-axis takes care of. So fundamentally, when we're optimizing something, when we're finding extremas, we're finding y values. Here's the stipulated definition of extreme values in general, of extrema. We're going to let c be a number in the domain of some function. We're going to call the domain d. Then f of c is defined to be the absolute max value of f on d if f of c greater than or equal to f of x for all x and d. And I don't think I'm going to read every single one of these things, but that's kind of the main idea. If in this definition we're using f of c to be whatever the max or min is, maybe absolute or local, depending on the definition that you're looking at. But the thing that I do want to highlight is the concept image for all of these definitions. The concept image of an absolute maximum is the highest y value. Right? The concept image of an absolute minimum is the lowest y value. For local stuff, the local max, for example, concept image I have is that it's the highest y value in its neighborhood. The definition is actually interesting to look at because it's almost verbatim what this definition says, right? This is almost the same thing. The difference is that instead of saying for all x in the domain D, we're saying, this is actually only true when x is near C, and I drew what that kind of means on the graph. All of these x values are near the C, right? In this case, C is x3. No matter what you plug into the function, right, you're going to get y values that are all going to be less than whatever your f of c is, right? Whatever that particular y value is at that point. Basically what it's saying is if you draw a bubble right around your high point, then it's the highest y value inside of that bubble. That's what it means to be local max, right? And we could say the same thing about local mins, which actually, and you'll notice that this is not only an absolute minimum, because it's the lowest y value on the graph, it also satisfies the definition of a local minimum, because in its neighborhood, it's still the lowest y value. And that brings us to some interesting facts, right, about extrema. This is the one that we just talked about. Sometimes y values can be both local and absolute extrema. They can satisfy the definition of both of them. Some graphs can have infinitely many absolute or local extrema. Think of sinusoidal curves, right? Anything that's a wave function that has a constant period and a constant amplitude has infinitely many absolute and local maximums and also infinitely many absolute and local minimums. Some graphs have a minimum but no maximum, and the opposite is also true, right? Some graphs can have an absolute max or a max in general and no minimums. And you can think about quadratics as examples of those things. And then finally, you can have some graphs that don't have extrema at all. X cubed is an example of that. This particular graph has no absolute extrema at all. And probably what I should do is put arrows on the end to really exaggerate that fact that this is a continuous function that's not on a closed interval. And so we're getting something that has no extrema at all. There's no hill or valley or any kind of high or low point happening inside of the graph itself, and it's falling to the left and rising to the right. But the one thing that we can say for sure is that if we're given a closed interval, there's definitely going to be an absolute minimum and an absolute maximum value. And in fact, this is a theorem. It's called the extreme value theorem. It says if f is continuous on a closed interval, a to b, then f attains an absolute minimum value, which we're going to call f of c, and an absolute maximum value, which we're going to call f of d, at some points c and d inside of your closed interval. Right? So c and d are somewhere inside a to b. And notice that we're saying that c and d are somewhere inside the closed interval a to b, which means that c and d could be the endpoints. They could actually be a, or they could actually be b, right, if we wanted them to. And that's the idea behind this theorem. It says that, listen, if you have a function that's continuous, you can pick the endpoints to be anywhere inside of this thing. Like maybe even originally we had truncated this, maybe it's a cubic function or something like that. You can pick any closed interval on this graph and you're still going to be able to find absolute extrema, even if the endpoints themselves are those absolute extrema. Now, the thing about this theorem, because I think it's tempting to think, oh, well, sweet, we can find absolute extrema for anything. That's not true. You can only find them when you have a continuous function on a closed interval. If you drop either one of those things, like here we're dropping continuity, so I drew a discontinuity in here, this graph actually has no absolute maximum. The highest point of the graph is an open dot, and we don't know what that number is, so this thing actually has no absolute maximum. So if you drop continuity, then you lose the theorem's conclusion. Similarly, if you drop closure, right, if you drop the closed interval, this thing's continuous. The way I drew it is actually probably continuous on the closed endpoint 0 to the opened endpoint, and really it's a vertical asymptote. There's a vertical discontinuity there. B, then now we lose the conclusion of the theorem as well, right? By making it not a closed interval, this thing continues up forever and ever and ever as it approaches that vertical asymptote, but this thing similarly has no absolute maximum. So you have to have those two things, continuity on a closed interval, for you to be able to conclude, okay, well, somewhere on this interval, there's an absolute maximum. There's a highest point and there's a lowest point. Right? There's an absolute maximum and an absolute minimum. But the main idea behind this theorem is that it tells us about the existence of absolute extrema. And the best part is we actually already know how to find these absolute extrema, right? We've been talking for a long time about finding when the slope of a graph is 0, finding when its derivative is 0. That's where extrema in general happen. Right? It's either your function is positively sloped and then it changes to negatively sloped. Okay, well, there's an example of having a maximum. Or your graph has negative slope and then it changes to positive slope. And again, that's where your graph has a minimum at that point. And in both situations, the slope at that point of change is 0. So all you need to do to find these extrema are differentiate your function, set it equal to 0, and see what you get. Right? What those x values are going to produce extrema in your original function. In fact, this is a theorem. Fermat's theorem says that if f has a local max or min at c, and if f prime of c exists, then f prime of c is equal to 0. So find where f prime of c is equal to 0. That's where you're going to have some kind of local extrema. But there's a couple of things to note here, and one of them is that the converse of this theorem is not true. So that means that if you're finding that f prime of c is equal to 0, that doesn't necessarily guarantee that there's an extrema at that point. And an example is the x cubed function. The slope is actually 0 at 0, but obviously based on the graph, just looking at it, you wouldn't say that there's an extrema that exists there. So this is only saying if there's a local max, then the derivative is 0, but we can't say, oh, where the derivative is 0, that's going to be a local max, right, or local min. And then it is also possible for f prime of c to not exist and yet still have an extrema at c on f. Think the absolute value function. Here, the derivative doesn't exist at 0, but this is for sure a local minimum. In fact, it's an absolute minimum for the absolute value function. Despite these things, though, Right, the theorem does give us a starting point for finding these c values, which, by the way, we're going to call critical numbers. A number c that's in the domain of the function such that f prime of c is equal to 0 or f prime of c does not exist. Those are things we're going to call critical numbers. And the points where it doesn't exist, again, would be something like a corner. Where a corner exists, there could still be a maximum when the derivative does not exist. So we can actually restate Fermat's theorem a little bit, and this is the definition that I think that we're going to go with. It says if f has a local max or min at c in the domain of f, then c is a critical number of f. And that takes into account a little bit more stuff. But again, the way that you read this is if it has a local max or min at c, right, then c is a critical number. But it doesn't say that if c is a critical number, then f is a local maximum or minimum. So again, you got to keep in mind the converse isn't true. The critical numbers are just giving us potential extrema. That's the way that you have to kind of look at this thing. Now, this is for all the students that have come from a pre-calculus class recently. And you might remember that when you're talking about polynomials, which are of this form, and I'm not going to read that, that's just the general definition of a polynomial, then in pre-calculus, we were able to talk about stuff like end behavior, possible number of real zeros, finding rational zeros with rational zeros test, completely factoring and finding x-intercepts sometimes, if we're given the right polynomial, how multiplicities affect the x-intercepts, the possible number of turning points for specific graphs. And we were able to use all of this information to get a pretty accurate, or maybe a pretty good idea of what the graph of our function looks like. But one thing that we were never able to do in pre-calculus is place extrema. Figure out where exactly a turning point would exist. But now we can, right? We can add to this list finding the extrema without having to look at the graph by figuring out where its critical numbers are and then determining, do those critical numbers give us an absolute or a local extrema? So this is where we're going to start for our examples for today. Example number 1, find the extreme values for f of x is equal to x cubed minus 6x squared plus 9x plus 2. Okay, so a polynomial here. First thing we're going to need to do is find the critical numbers, because as we know, Fermat's theorem tells us, if this thing has any local extrema at all, it's going to come from critical numbers. Polynomials don't have critical numbers where the derivative doesn't exist, right? Polynomials are always nice and curved functions, and the derivative of a polynomial is also going to be a polynomial, and that doesn't have any, places where the function doesn't exist. So the critical numbers in this case are just going to come from the zeros of the derivative. And again, those are going to be places where we're potentially having some local extrema. I took the derivative just using the power rule here, and then I factored it because factoring polynomials is one easy way to figure out where it has zeros, because I need to set it equal to 0 to find what our critical numbers are going to be. So that means that our critical numbers are at 1 and 3. So the next thing I'm going to do is I'm going to actually figure out what f is at these critical numbers. So I plugged in 1 and I got 6, and then I plugged in 3 and I got 2. And remember, these critical numbers are where the derivative is 0. Okay, so they could be high points and low points. It could be a situation like this, where you've got a slope of 0. That's not the best graph ever, but think x cubed. We could have these things not being a maximum or minimum, but if they are, we need to know what their y values are, and that's why I'm plugging them in to figure them out. Now, to actually figure out if they're minimums or maximums, right, to figure out which ones are mins and maxes, then you have to perform a sign analysis. Okay, so that's what this is. Now, we've talked about sign analyses before, but you don't necessarily have to perform one if you know what the end behavior of the graph is. And I'm circling this, but we're doing a sign analysis on this. That's the sign analysis for this is what's here, because I need to know where the derivative is positive and negative to know whether f is increasing and then decreasing, and again figuring out which is going to be a maximum or a minimum. So that's what I did here. I performed a sign analysis on 3x squared minus 12x plus 9, which I factored into this. So I'm not going to go over the sign analysis since I've talked about it in a previous video, but just remember that what we're doing is we're looking at the overall sign of f prime by plugging in some test values that are inside specific intervals. Since we know the graph intersects the x-axis at these values, then f prime of x, right, or rather the function itself, right, because that's what we're talking about. This is for x, f prime of x is changing its sign at all, right, is crossing the x-axis or not. So during my sign analysis, I figured out that the graph is positive from negative infinity to 1, and then it changes to being negative from for the interval 1 to 3, and then it changes again to being positive on the interval 3 to positive infinity, which means that there are some maximum and minimum values happening, right? The slope is changing from positive to negative. Then the slope is changing from negative to positive. That's a maximum and minimum respectively. If this critical number stuff, if this sign analysis had given me negative and then negative again, okay, well then there wouldn't be a minimum there. It would be something like, well, you've got a negative slope and then it levels off, has a slope of 0, and then it's negative slope again. And that's certainly not a situation where you have an extrema. So again, this is Fermat's theorem only says these critical numbers give you potential places where a minimum or maximum could happen, but it doesn't guarantee that they do. In this case, we lucked out. 1 is giving us a maximum, 3 is giving us a minimum, because we go from positive to negative here. So that means that, on the graph, something like this is happening, and then we go from negative to positive for 3, so then something like this is happening. So we're getting this type of case. So therefore, f of 1 is equal to 6 is a local maximum, because that's where we're changing from positive to negative, so something like this is happening. And f of 3 is equal to 2 is a local minimum, because we go from negative slope to positive slope, so something like this is happening. In fact, I graphed it. This is what the graph ends up looking like. You'll notice that these are only local extrema because this particular function, it's not a closed interval, right? So we're not getting absolute stuff. The extreme value theorem's not happening in this. It's not applicable to this case. Here we're just practicing how to find critical numbers and then find local extrema. So no absolute extrema in this one, especially because it's an odd degree polynomial, so one side's falling and one side's rising. So we could conclude that almost right away before having done any of this stuff that we did already. But if I replace the arrows with endpoints, right, and so now I have a closed interval on this function, then now we would have absolute maximum and absolute minimum values. But the thing that I want to point out about those absolute maximum and absolute minimum values is that they wouldn't have come from critical numbers. Well, I guess one of them would have, right? This one would have. But the absolute minimum is here. That's an endpoint. That doesn't come from a critical number. And so if we're working with a closed interval and we're trying to find extrema that are absolute, we can't just focus on critical numbers. We're going to also have to look at some endpoint stuff as well. So in example 2, it says find absolute extrema for p of x, which is this x minus 2 sine of x. It's this trigonometric function. But crucially, I've given us a closed interval. So we want to find the absolute extrema on this closed interval here. Well, to do that, we're going to have to use the closed interval method for finding those extreme values. Also important to point out, we could find local extrema, but that's not what the question here is. We're asked to find what the absolute extrema are for this function, which means that I don't need to necessarily perform like a whole sign analysis or anything like that in a case like this, because we're just looking for the highest and lowest points. To do that, you have to use the closed interval method. It says to find absolute extrema of a continuous function f on a closed interval a to b, you first need to find values of f at the critical numbers of f on the open interval a to b. So we're going to do normal critical number stuff that we just did like on the first example. But again, not all the way through sign analysis, just finding critical numbers. 2, we're going to find the values of f at the endpoints of the interval, which means we need to find f of a and f of b. And then the third thing we're going to do is we're going to look at that list of values that we just produced from 1 and 2. And then the largest of those values is the absolute maximum. The smallest of those values is the absolute minimum. And that's it. Oftentimes when we're doing problems where we're maximizing or minimizing, we're actually looking for the highest maximum or the lowest minimum. And so we don't necessarily care about where exactly all the different high points and low points are happening, just what the biggest high point is and what the lowest, the smallest low point is. Okay, so first we need to find what our critical numbers are, which means we need to differentiate this thing and set it equal to 0. Here, the derivative of x minus 2 sine of x is 1 minus 2 cosine of x. And then I solved for cosine of x. Cosine of x is equal to 1/2. At this point, I would need to take the arc cosine of both sides. And here, what we're finding is essentially a reference angle. And I'm trying to figure out what angle on the unit circle produces an x coordinate of 1/2. That only happens in one location for arc cosine, and that's at pi over 3. But our interval is from negative pi over 2 to pi. So we can use the reference angle, and we're trying to figure out when the cosine of x is positive 1/2. So the reference angle is actually one of my solutions. And then the other one is at negative pi over 3. And that's it. Those are the only two places from negative pi over 2 to pi that make cosine of x equal to 1/2. Now, again, what I'm trying to do is find absolute extrema, so I'm going to find the f values at negative pi over 3 and pi over 3, and that's what all of this work is. This is just function evaluation, and so, okay, I got these two numbers here. Negative pi over 3 produced a y value of 0.684, and pi over 3 produced a y value of negative 0.684. Second thing we need to do is we need to evaluate p at its endpoints. So again, just some function evaluation stuff. P of negative pi over 2 gave me approximately 0.4292, and p of pi actually gave me pi back. So if I'm trying to determine what the absolute maximum is, all I'm going to do is I'm going to look for the highest y value. And that happens at p of pi, which is pi. So p of pi is the absolute maximum, which is pi. And the absolute minimum is the smallest of this list, which is negative 0.684. Okay, so hopefully that was helpful. I kind of feel like I rushed through some parts, but hopefully the extreme value theorem makes sense and Fermat's theorem makes sense. If we're going to paraphrase everything that we learned today, right, the first thing is that absolute extrema are for sure going to exist on a function that's both continuous and exists on a closed interval. That's what the extreme value theorem says, and we just put it into practice here. We found those extreme values, minimums and maximums. And then Fermat's theorem says, hey, listen, if there exists any minimums or maximums, any local extrema on this graph, they're going to come from when either your derivative is 0 or your derivative doesn't exist. Those things are called critical numbers. Finding the critical numbers doesn't guarantee that at every critical number you have a local minimum or maximum, but it does say that, hey, it's going to come from this list of critical numbers that you did find. They are potential minimums and maximums, if they exist at all. So if you guys have any questions, please shoot me an email or leave a comment below. Thanks a ton for watching, and I'll see you in the next one.